Hey folks, Professor Fiore here, and it's time for Network Fun number 3. If you haven't watched the first one, definitely want to watch Network Fun number 1 before you watch this one. There's some really useful clues in there. Network Fun number 2 extended the idea into 3 dimensions. Well, we're going to go one better than that in this one. We're going to go out to 4 dimensions. And I mean 4 Euclidean dimensions. None of this 3D space with an extra dimension of time. 4D space-time, right? Sci-fi's wonderful thing. No, we're going to do something much more interesting in my mind. Something that I loved playing around with years ago, still do. Make little 4-dimensional models of things. Well, they're actually 3-dimensional models of 4-dimensional things, just like the way you would try to draw a cube, which is a 3-dimensional thing, on a 2-dimensional sheet of paper, right? You don't have the 3rd dimension on the piece of paper. Well, you don't have the 4th dimension. And, if you're going to try to make a 4D sculpture, right, you have to kind of warp things. So here's what I'm talking about. We're going to start with the simplest regular shape we can get, which is a triangle. We are ultimately going to make something called a hyper-tetrahedron, meaning hyper referring to the higher dimensional 4D, 4-dimensional shape. Tetrahedron, of course, is a 4-surface thing, right? Tetrahedron is another way of saying it's a triangle-based pyramid, right? Unlike, the Egyptian pyramids or the Mesoamerican pyramids, which have a square base, right? A tetrahedron you would think of as a pyramid with a triangle base. So we start with a triangle. Duh. All right, so 3 lines, right? A line, of course, is a 1-dimensional entity. It just has 2 points, right? You got a length. There's no width. There's no thickness, no height, okay? You just have a length. So we take 3 of these, and we arrange them as such, right? So we wind up with a triangle, okay? Could be equilateral, just for ease of drawing. And I'm just going to label each vertex here A, B, and C. Now, to get to the normal tetrahedron, we're going to have to add a 4th vertex. And, where do you want to do that? How do you want to do that? If I only have a 2-dimensional space here, right? My screen, piece of paper, I can't make something that's orthogonal to this surface, which is really what I want to do. I want something that's like halfway between this screen and your face, okay? And then I can draw, the other edges, so to speak. So I have to kind of warp that. But we're used to seeing things, on paper, on TV, whatever, that do that. Right, so we would wind up with something like this. So take the A, B, and the C, and I'm going to sort of warp it and add vertex D, right? And we get this, right? So you've undoubtedly seen this kind of thing before. So we now have, instead of 3 lines creating a triangle, we now have 4 triangles creating the tetrahedron, right? So we had 3 lines in 2D to make this triangle. Now we have 4 triangles in 3 dimensions, right? So if you don't see it, right, got triangle base, you have this triangle, which is one face, you have this triangle, which is the other face, and then you have this big triangle, right, which you might visualize that as being in the back, all right, as your 4th triangle, all right? Okay, so just as a triangle is a face on a pyramid, on a tetrahedron, a tetrahedron or pyramid would be the 3-dimensional face of a 4-dimensional hyper-tetrahedron. Right? Is your mind appropriately blown? All right. How do you draw that? Well, same deal. I have to come up with the 5th vertex, E. And this is like doubly ugly because this is actually easier to do if you were to sort of sculpt this. If you were to get some sticks and glue them together, this could make a lot more sense. But now I actually have to do a 2-dimensional representation of a 3-dimensional representation of a 4-dimensional object. So, the angles on this are like totally messed, okay? But you can imagine. So, where do I put it? Where do I put this fifth vertex? It doesn't really matter because everything is going to get distorted in space. I could put it over here, I could put it over here. Like I said, it'd be nicer if this was actually drawn in 3 dimensions, sculpted rather than just drawn on a flat surface. But I'll just put it somewhere convenient, like maybe right smack dab in the middle of this. Bonk. All right. So there's E in the middle, and I've chosen these sort of thinner weighted lines to make it a little easier to see. So in the preceding, we had 4 triangles making up the tetrahedron, right? Again, the base, this side, and then the big side in the back. So you got 4 triangles making this up. Well, so 4 2D things to make up the 3D thing. Now you have 5 3D things to make up the 4D thing. So we have a whole bunch of normal tetrahedrons to make this up, right? So first of all, on the base, right? So A, B, C, and E you could kind of think of that as sort of like a squatty tetrahedron, all right? How does this deal with electronics? Just hang on, we'll get there. There's one. Now you could think of A, C, and D as being another base, with E being the top vertex, right? B, C, and D being another base, with E being the top vertex. A, B, and D being a base, so this is like on the opposite side, with E being a vertex. And then, of course, you've got the A, B, C, D is your 5th one, right? So you have these 3-dimensional faces, so to speak, that would make up this 4-dimensional tetrahedron. Okay, so this is where it all comes in with the electronics. We're going to make each one of these lines a resistor, and they're all going to be equal. Right? So I'm going to have this hyper-tetrahedron of resistance. So, network fun number 2, you thought was fun because we had a cube. Oh man, check this out. I got a cube of resistors. This is like totally wacky. Yeah, well, that's child stuff, right? So now we have a 4-dimensional hyper-tetrahedron. Okay. So off we go. Okay. Now here comes the fun part. And that's not analyzing it, which is fun enough. But the fun part now is trying to draw this in your simulator. Because as I mentioned in network fun number 2, the simulators that we use, the electronic CAD stuff, is designed pretty much rigidly for this 2-dimensional representation. Everything's oriented left, right, up, up, down, right? It's either horizontal or vertical. It's hard to draw stuff at angles. So it's difficult enough to draw something that's 3D, but what about try to do something that's 4D? And let's face it, you don't really need 4-dimensional kind of stuff, to design a consumer electronic product. But again, the idea here is to get out of your normal mode of thinking, think differently. So how do we do this? Well, here was my approach. So again, I've got this like ABC I'm going to use as the base, and then D is the top, and E is this 5th one that we added as we went through the steps, right? So you might remember, we started with a triangle ABC, and then we went ABCD to make it 3D, and then we added E to make it 4D, okay? So here we go. All right, so here's A, B, and C. So A to C, right? This was like the back of the triangle. So there's your 1K. A to B, there's a 1K. B to C, there's your other 1K, right? So these 3, that would make the base. And then we put D up on top, all right? So I need a resistor going to each one of those. So there's A to D, there's C to D, and coming back around here, there's B to D. And then in the middle of the whole thing, we had E, and there's a resistor going to each of the other 4, right? Down to A, B, C, and up to D. So just to compare, right? E, we had these going like so. All right, so if you study this, if it's not immediately apparent, just flip back and forth, pause the video, look at this, and you'll see that the construction is the same, right? Topologically speaking, they are the same, right? But you got to admit, the other one looks so much more intriguing. This is just like, what? Well, It's warped. It's constrained into 2D and left, right, up, down. Okay? All right. So now comes the triple fun part, or maybe it's the four-dimensional fun part, and that is we're going to connect up a current source and a ground. Now, I have arbitrarily chosen node A and node C. It turns out you can pick any two nodes, and you're going to get the same result. So you could take the current source and run it into B and ground E. Or you could run the current source into D, right, and ground C like I have here. Or you could, ground B or ground A, or run the current source into E. It doesn't matter. So you got 5 of these, put the current source into one of them, and ground one of the other 4. You're going to get the same result. So our question again is, what is this voltage? What is the voltage that we see off the current source? Okay, so we could pause the video, and get out a piece of paper, baby. Apply Kirchhoff's current law, Kirchhoff's voltage law, right? Kirchhoff's really, really good voltage idea, which always works, and Ohm's law, and see what you can come up with. In the meantime, I'll patiently wait. But maybe I won't. All right. If you're compulsively curious and you just have to do it, don't pause the video. I'll go through this. All right, so how do we approach this? Well, if you watched Network Fun number 1, and if you didn't, shame on you, because I told you to watch it first. But in any case, there's a clue there. I drew it like this for 2 reasons. One, because I wanted to, kind of draw something where the nodes reminded us of the final drawing there, but also because of the way the currents are going to split out, right? So I got this 10 milliamp current source coming into node A, and there's really 4 ways it can go. It can go through R1, R3, R7, R5. And of course, they recombine, right? Those 4 currents recombine, KCl, come back to ground. Well, I want to focus on the top 2 and the bottom. In other words, the current coming into R1, R3, and R5. Notice in those 3 cases, you've got a 1K resistor, a node, another 1K resistor, and then you're back to ground, right? Same thing here with R3 and R4. Same thing here with R5 and R6, okay? This one, R7, is sort of the odd guy. It's just the 1K, a single 1K going right to ground, all right? Now, what we see is symmetry as far as, if I was an electron, okay, you're an electron. What do you see? What do you experience? What's the least resistive path to ground? Well, there isn't one. They're all the same as far as these 3 are concerned. It's R1, R3, R5. Those currents are going to wind up being the same because you have the same situation going on back to ground. You've got the first resistor, then a node, okay, which is going off to these, resistors going off to these other nodes, and then another 1K, which brings you back to ground, which is where you're trying to go. Well, if these things are symmetrical, then the currents through R1, R3, and R5 would have to be the same. And here's the important bit. That means the voltage drops across these 3 resistors have to be the same, which means that node voltage D, node voltage E, and node voltage B all have to be the same. And what did we discover about that? Well, if VD and VE are the same, then the drop across R8 is 0, which means there is no current through R8. R8 may as well be infinity. And the same thing is true down here between VE and VB, right? R9 sees nothing. It sees no differential voltage, so there's no current. And lastly, when we go between D and B, same result, there's no potential across R10, so that current is 0. So all the current that goes through R1 goes through R2. All the current that goes through R3 goes through R4. All the current that goes through R5 goes through R6. So in other words, this looks like 2K, that looks like 2K, that looks like 2K. So what you really have here is a 2K in parallel with a 2K, which is 1K. That's in parallel with a 1K, 500 ohms. And that is in parallel with another 2K. So 500 in parallel with another 2K would be 400 ohms, right? And it doesn't really even really matter what the value of R8, R9, and R10 happen to be, right? Because like I said, there's no current through them. So given that, 10 milliamps through that resistance is going to give us 4 volts. So let's give it a try. See what we get. All right, there's our 4 volts. Now let's check the currents, okay? Oh, and by the way, before I go any further, because there's only the single 1K here, we would expect this current to be twice the currents in these other 3. So coming in, so there's 2 milliamps, 2 volts. Come through here, still 2 milliamps, 2 volts. Look at our 3, 2 milliamps, 2 volts. Look at our 4, 2 milliamps, 2 volts. Our 5, 2 milliamps, 2 volts. Our 6, 2 milliamps, 2 volts. And of course, the R7, the odd guy in the group, 4 milliamps, 4 volts, because it's half the total resistance. These other things look like 2K. Let's check the sort of bridging resistances here, right? 0 volts, 0 amps, 0 volts, 0 amps, and 0 volts, 0 amps, right? So, as I said, you could pick any 2 nodes, right? R7 isn't quote unquote special here. I called it the odd guy out, but it was only because we chose nodes A and C. If I chose the current source to go into node D and the ground was, let's say, on node E, okay, what ends up happening? Well, R8 would be analyzed kind of the way R7 is, right? That would be the sort of odd guy out. And then you would have an appropriate combination back here. So, you would have to go through a couple of things to get, just like here, you have to go through a couple of things to get to ground. It would be the same sort of result. So, and you can see this probably a little better when we go back to the sort of wireframe thing here, right? Pick any 2 nodes. So I think, what did we have back there? A and C. All right, so A to C. So that was the 1K. And all these other things, we can see, I can come up to here and down. I can come over to here and back. I can come up here and back, okay? If it was D to E, it's the same sort of thing, right? The straight line is that, but you could go from D to A to E. You could go from D to C to E. You could go from D to B to E, and so on and so forth, all right? Pick any 2, you get the same result, all right? Trick is, if there is a trick, all the resistors in here are the same size, right? If you change the values, you no longer have symmetry, and you have to do something else, right? You could solve this with nodal analysis. All the circuits we've looked at in Network Fun, you could solve with nodal analysis. But the idea, of course, of this sequence is to kind of break out of that and look at something different. So now you can go brag to your friends and talk all about the analysis of hyper-tetrahedrons. And of course, they'll look at you like you have 5 heads. But if they do, tell them that they should look at you like you have 4 heads because it's 4-dimensional. All right, until next time, this is Professor Fiore saying, have a good one.